This is probability distribution. So you have different categories or classes or words or tokens, and each one has some probability to be picked, and all of them add up to 100%. So in this case, this here, whatever the number it corresponds to, would have highest probability. So when our large language model is learning, we are trying to adjust these probabilities so the correct next token has highest probability. So that thing happens during reinforcement learning as well, when we are teaching it to reason. And we use KL divergence because we don't want the new changed probability distribution to be so different than the previous one, because it might be wrong. So KL divergence is gonna constrain how much one probability distribution can change. So there is forward KL and reverse KL. And this paper is saying, okay, we don't know, first of all, which one to choose when reinforcement learning, or there is no rule book. There are other issues where there are no standardized rules as well. So forward KL is gonna say what is the KL divergence from old policy to the new policy, or I can also say how much does new policy pi theta diverge with respect to the old policy from the old policy. And this is the formula that looks kind of complex, but it just says you want to, or the new policy should assign non-zero probability to every single class that old policy has some probabilities. So if old policy had some class with some probability, and then for that class new policy assigns 0 probability, then there will be huge divergence. So we want to actually remove, or we want to make sure that every class or label or token that has some probability in old also has some probability in new. That's what forward divergence does. This encourages exploration, because now so many different things are going to have at least a bit of probability. So you can use this in environments or models where you're not sure what is the correct way to solve the task. So this way you can explore many different ways. Or you can also use forward KL divergence to preserve very well-rounded model that can generate many different things. For example, if you have some prompt and it can generate 3 possible, for example, or more, but let's say these 3 examples. In the old policy, the new policy, you also want it to be able to preserve, to generate multiple different examples. You don't want it to just now put very high probability to this first example and then 0 probability to maybe one of these or 2 of these. So you want to preserve divergence as well you can do it this way. Preserve the probabilities and the possible answers generated. And reverse KL is gonna be opposite. Here, the lowest divergence, the lowest error will happen if the new model looks at old model and then looks at the highest probabilities and then assigns even higher to those. And you can do like very low or zeros on the others. So, to summarize, reverse KL will be best if the new model makes high probabilities even higher and low even lower, which is opposite of the previous one, where it actually made everything more equal or uniform. So we have this ratio of the new probability over old probability distribution. And we want this ratio to be as close to 1 as possible, because then log of 1 will be 0. And if you look at the formula here, so we want to make this result, KL divergence, as small as possible. So if we have this log of this ratio, if it's log of 1, then it's going to be 0 here, so this KL divergence will be 0. Let's take a look at an example. The best programming language for beginners is, and then the entire vocabulary can be Python, Java, or C++. And then old policy would assign 60% to Python, 30% to Java, and 10% to C++. And let's compare 2 different types of new policies. Let's say new policy, Pi A, decided that actually Python is the best, and now it's 90%. And these other two are just 8% and 2%. So this is big difference. Now this has a lot higher and this has a lot lower probabilities. And the second policy made the Python a bit more likely. So now it's 70% instead of 60, kept Java at 30%, but set C++ at 0, while it was just 10%. So this is a bit higher, this is same, this is a bit lower. And here we have just the formulas for reference. So we have forward KL and reverse KL. Forward, the only difference is this all policy divided by new, and here we have new policy and new policy divided by old. And this sigma is encapsulating the whole thing because this is in brackets. So log of this times this and then add all of them. We'll see what that means. Join my school to become AI researcher. It's free for now. We have all of these courses. I'm gonna make it paid soon, so hurry up. Link below the video. So forward KL divergence actually doesn't want us to give 0 probabilities to things that had some probability here. And you will see that this second example in forward KL divergence will have infinity divergence, which is a huge number. That's a lot of divergence and we don't want that. That's because we have 0 here. We are dividing with 0. And so log of infinity, we have infinity. So this is step-by-step example, you can check. But we just define old policy times log of old policy divided by new policy, but new policy is 0, which will give us infinity. So we don't want it to be 0 if it was something before. That's what forward KL divergence will do. And in this example above, it will not throw such an error. So here it's just a bit of divergence, but it's small number, it's not a huge number. So this one is actually quite acceptable and good. This acts as a safety net, preventing the model from completely forgetting anything that was once considered plausible. Okay, so that's forward. Let's see now reverse KL divergence. This one will punish if the new model assigns higher probabilities to what old model considered very unlikely, very low probabilities. I will show you an example. Let's say we have another coding language, assembly, and here it's 0.1% or 0.001, so highly unlikely that this is a good language. And let's say that in first example it's unchanged, in second example it goes to 0.2, big increase. Let's see what happens with our KL divergence. So we have a log of the new probability over the old probability that was very, very small. So this will result in a big number. So we will have a log of a big number because we're dividing with a very small number. So now our KL divergence will go up a lot. So that's what reverse KL divergence does. You can see that I also changed these other probabilities, but their KL divergence is very small here and here as well. Very small compared to this, that's 1. So changing these others did not influence too much, but here changing very small one would make division with that very small number, which would explode the KL divergence. Even here, if C++ suddenly went to 0.8 as opposed to, and it was 0.1 previously, this will also be a big number, log of 8, which will still be big number here. So small probabilities, even 10%, can, if you increase that by a lot, it will cause a lot of divergence. So that's how forward and reverse KL divergence work. And in this paper, it was explained that there was no set rules on when to use which in reinforcement learning. Another issue is we don't know when to use this normalized versus unnormalized distribution. So normalized is when all of the probabilities sum up to 1, to 100%. And unnormalized, the probabilities are also positive, but they don't necessarily sum up to 100%. So they are scores rather than probabilities. So our forward and reverse scale divergence works on the normalized when they sum up to 1. And now I'm just explaining different things that are done in the reinforcement learning, and later we will explain how to improve them as per paper. And for unnormalized scale divergence, we would measure not only the shape as before, but also the total mass. So if these scores add up to some number in one policy and add up to another number, so we also measure divergence there. So these are the problems that paper says that are still kind of not clear what we should do. Like, should we use forward or reverse? Should we use normalized or unnormalized? How should we use estimators that I will explain now? So what we want to do is we want to look at the entire output or sentence, for example, of the LLM as one sentence amongst all possible sentences, and that one sentence has some probability to happen, and every sentence has probability to happen. So this can be used, for example, if we want to ask, did the model solve the math problem correctly? So we just look at the entire sequence as a single thing that has single probability to happen. We can use estimators to estimate probability of this sentence happening or this whole output happening. But I'm first going to show you what estimators are on a simple example. And they are estimating, for example, KL forward KL divergence, or some estimator is estimating reverse KL divergence. And they could be, for example, faster or easier or better way to estimate KL divergence with less computation, etc. So K1 estimator is used to estimate normalized reverse KL. Normalized means probabilities add up to 1. And the formula for K1 is just log of new probability over old probability. So the formula is a bit different than the reverse KL, but it's gonna serve the same function as the reverse KL. So if we had very small probability before and now we assign very high probability, this calculation, the estimator will be very high, so it will punish the same thing the reverse KL is punishing. The paper shows that also K3 is not just an estimator, but it shows the exact value. It's a direct value of unnormalized KL divergence, not just an estimator. And there is a mathematical proof down below. So you can, so this is the formula. It's y minus log of y minus 1. And y, now depending if you want to use this as forward or reverse, y can be old over new policy or new over old policy. So for reverse, it's gonna be old over new. And it's gonna do the same thing as I was explaining. So mode seeking or zero forcing, depending on if it's reverse or forward, it's gonna do the same thing. It's just for when probabilities don't add up to 1, you can use K3. Let's now look at off-policy training and importance sampling. Let's say you have an LLM, training it to solve math examples. So you generate 1,000 solutions and it gets +1 for correct and 0 for incorrect answers of those 1,000. And then you update the parameters of this policy of this LLM. Policy is the LLM based on this feedback. So it's more likely to generate correct tokens, correct answers, and less likely to generate incorrect ones. So you change the probability distribution of tokens based on the previous text of the question, of the math answer of the question, etc. On policy, here you would throw away all of these 1,000 examples because they're generated by the old policy. Now you have a new updated policy, updated LLM, updated weights. Now you need to use that to generate data so you can improve that. This is the main drawback of on-policy algorithms like reinforce, because they are sample inefficient. They use these samples just to do one gradient update. So solution is off-policy. So in off-policy, the LLM that's learning, it's different from the LLM that's generating data. So now you can use the old policy to generate 1,000 solutions again, but you can use those 1,000 to do multiple gradient updates to the new policy that you are changing. So first you do a single gradient update to make probabilities better of the tokens, and then you calculate how this new model would assign the probabilities to those same tokens. So this is a lot faster. You don't generate token by token, you don't do all of the repetitions, you just do very fast check to see how the new updated model would assign probabilities. And maybe it would assign higher probabilities now to the better tokens. And so you repeat that again. Maybe those probabilities need to be even higher. So you again update them to make those probabilities that are correct even higher, for example. And then you loop like that. So instead of generating all of the words again, you just check quickly the new probabilities the new updated model would give to those existing generated words. Actually, guys, I think I will end the video here. Join my school to become AI researcher. We have all of these courses. It's free for now, so hurry up, and because I'm gonna make it paid soon.